Hi, my name is Ira Globus-Harris, and today I'm going to talk to you about my work on lexicographically fair learning with Emily Diana, Wes Gill, Michael Kearns, Aaron Roth, and Saeed Sharifi at the University of Pennsylvania. As a general rule, we'd like our algorithms to be equitable across different groups of people. But what is meant by this varies. Today, I'll be talking about a new definition of fairness we propose, approximate lexicographic fairness. I'll discuss some properties of this fairness form, and we'll introduce Oracle-efficient algorithms for it. One common definition of group fairness is equality of group errors. The algorithm should make the same number of mistakes over all groups. Thus, if gamma I is the group error of group I, hypothesis 1 would not be fair under this definition, since group 1 has substantially more errors than the other groups. But hypothesis 2 would be. One potential problem with this definition is that often, in order to achieve equal group errors, the error on easier-to-predict groups may have to be artificially inflated. Thus, while the group errors are equal, the overall social welfare is worse. An alternative notion of group fairness is mini-max group fairness, which posits that the number of errors made on the worst-off group should be minimized. Here, hypothesis 2 is a minimax solution, providing that the minimum error that group 1 can achieve is 0.2. A natural extension of minimax fairness is lexicographic fairness, or lexi-fairness for short. This requires that after you minimize the error of the worst-off group, you minimize the error of the second worst-off group, subject to the minimization of the first worst-off group's minimization, and so on. For example, here we would first minimize the error of group 1, then, subject to its minimal value, minimize the error of group 2, and subject to those two minimizations, we minimize group 3's error. This seems like a pretty straightforward generalization of min-max fairness, but there's a catch. We can't efficiently get a true minimization of the maximum group error, just an approximation that guarantees we're within alpha of it. So how do we generalize this notion of approximate minimax fairness to the lexifair setting? Can we require that the ith group in the approximate solution has error within alpha of the ith group's error in the true lexicographic solution, like here? It turns out this is not possible due to inherent instability. To see why, consider what happens to the minimization of errors in the following case, where the true lexifair solution has 0.5 error on the first two groups and 0 on the third. Here, we'd like to find an approximate solution where the first two groups have solutions less than alpha above 0.5, and the third group has error less than alpha above 0. So, say we approximately minimize the maximum group error and get something alpha worse than 0.5. So far, this is acceptable. But because the first group had slightly worse error, we might be able to greatly improve the second group's error, say to 0.25. This is still fine since it's better, not worse, than the lexifair solution. The problem comes in minimizing the third largest group error. Because the second group error is so much lower, there may be solutions where the third group error is much higher. But in the true lexifair solution, the third group error was 0, right? So we can't guarantee that our approximate solution puts less than or equal to alpha of the error rate onto group 3. So we can't meet this definition. Instead, we provide a stable definition, where the error of the jth group is defined recursively in terms of the previously approximately minimized group errors, which are bounded by some vector of epsilons, which are component-wise less than alpha. Using this stable notion of approximate lexi-fairness, we derive Oracle-efficient algorithms. We rewrite the feasibility problem as a minimax problem, show that the minimax theorem applies, and then play a two-person zero-sum game between a learner, who plays a no-regret online learning algorithm, and an auditor, or dual player, who plays a best response to the learner's actions. We find lexifair regression models by having the learner play online projected gradient descent, and find classification models by having the learner play follow the perturbed leader. Overall, we introduce a stable definition of approximate lexi-fairness. We derive Oracle-efficient algorithms that meet this definition, demonstrate that they are efficient when the underlying ERM problem is convex, and give generalization guarantees for lexi-fairness. Thank you.